Hey there, welcome to lesson 2.2, Ions, Isotopes, and Atomic Mass, oh my. In this section we will continue our study of the atom. We've already disproven one of Dalton's points in his atomic theory. We have learned that the atom is not the smallest particle of matter after all. There's actually smaller things inside the particles called electrons, protons, and neutrons. Let's see if we can disprove anything else. In 1912, the English chemist Frederick Soddy made an interesting observation. He knew that uranium decayed into lead, and they likewise knew the atomic number of uranium was 92 and the atomic number of lead was 82, a difference of 10 obviously. When uranium decayed into lead though, there weren't 10 steps, there weren't 8 steps or 1 step, there's actually 40 different steps instead. And so the question was, remembering that radiation is like leprosy, how do you lose 40 different parts out of something that's only different by 10. That just didn't make sense. A year later, J.J. Thomson of his cathode ray tube fame found that when he used neon atoms in his cathode ray tubes and he brought a magnet up to them, they were actually split into 2 beams instead of 1. And so here is our cathode ray tube again. And so if that is 1 beam, imagine there'd be a second beam that maybe traveled a little bit farther than the other one. Okay. What would make this happen? Well, as you know, if you ever tried to push someone on a merry-go-round or in a swing here, the more massive they are, the harder they are to push, the more they want to keep their motion here. And so in this case, the blue particles would be more massive because the magnet would exert the same force on both of them, but the blue ones being larger would be more difficult to turn, and so they would continue going straight more and impact at a farther point. The green particles, though, because they've been easier, had to be smaller in mass, and so therefore these neon atoms had to exist as 2 different masses, not just 1. And so that meant that no, all neon atoms could not be the same. In fact, there had to be at least 2 different kinds here. And this was confirmed a few years later than when the English chemist Francis Aston developed the first mass spectrometer, which basically worked as J.J. Thomson's magnet and cathode ray tube. You put a very strong magnetic field around some charged atoms, and the atoms will bend their paths. The more massive they are, the less they bend, and the lighter they are, the more they'll bend. For more information, you can take Physics C, Electricity and Magnetism. Until then, you can just take my word for it. And so, in conclusion, then, Mr. Dalton was wrong on one other point as well. Not only were atoms not the smallest particle of matter, but all atoms of a given element were not identical. They had different masses. And so some vocabulary you're probably familiar with. Isotopes are atoms of the same element that have different masses. So what causes an isotope to have a different mass? Well, as we know, there's only 3 particles to an atom: the proton, the neutron, and the electron. The electrons, we have already said, don't really have much mass at all. Okay? And so if you have a different number of electrons in your atom, that wouldn't really change its mass. Protons, as we know, determine what element you have. It determines the atomic number. And so if you had a different number of protons, you wouldn't have the same element. And so that leaves neutrons in. And so isotopes have different masses because they have different number of neutrons. So we'll just add that on there. The prefix iso, if you're familiar, means same. So it's the same tope, whatever a tope is exactly. So the same element but different masses because a different number of neutrons. Behaviorally, they behave very similarly. The isotopes of the same element will react pretty much identically with anything else. The only difference you might see is the heavier ones might move a little bit slower, and their bond energies might be a little bit different, but otherwise they're exactly the same. So then going back then, if you change the number of neutrons in an atom, you get a different isotope. If you change the number of protons in the atom, you get a different element. What happens if you change the number of electrons in an element? Well, then you get what's called an ion. Right? And so an ion is an atom with a charge. And it has a charge because normally your number of protons your number of positive things is equal to your number of electrons, symbolized by E negative here. For an ion, though, that's not the case. Either the atom has gained electrons or has lost electrons, but it's no longer equal to the protons. Okay. Now, ions do have very different properties from the neutral atoms. Sodium, for example, if it has all 11 of its electrons, it is very, very reactive. In fact, as you've probably seen in Mr. Hyde's class, if you throw it in water, it's going to explosively react and burst into flames. If you remove just one of those electrons, though, you're going to get sodium plus. Sodium plus is basically inert. It doesn't do much. In fact, it tastes pretty good on French fries. Right? And so you can see that removing just one of the electrons from sodium makes a huge difference in properties. And later in the year, we'll learn a little bit more why that's true and why that one electron makes such a big difference. And so then we have a few more definitions to clear up here. We have the little chart. Atomic number of protons in an atom. And how to calculate it? Well, it's pretty simple. You just count the number of protons. That ain't hard. Of course, it is hard because it's hard to see a proton. They're really small. So instead, we turn to the periodic table, and that is the whole number on the periodic table. Usually, it's a different color, like red, or it's bold, or large, or something like that. So it's a whole number in the periodic table. So for example, hydrogen, the first element, has atomic number 1 because it has 1 proton. Helium has atomic number 2 because it has 2 protons. And tantalum, number 73, has 73 protons. The next number is the mass number, represented by A. Oh, don't ask me why atomic number is represented by Z. Makes no sense to me. Mass number A, I don't know what those guys were thinking here. But what the mass number is, it's the number of protons plus the number of neutrons. Basically, it's the mass of the atom, because as we talked about earlier, the mass of the electron is so small, just ignore it. And so if you want to know the mass of the atom, you just add the protons and neutrons and ignore the electrons. And so how to calculate it is you just add the two. So it's number of protons plus number of neutrons. Okay. How to find it on the periodic table? Well, you don't. You can't. There's another number up there we'll talk about soon. That's the atomic mass. Oh, actually, we'll talk about it right now. What the atomic mass is it is an average mass of all isotopes of an atom. We'll get to how you calculate it below in part 2. There's a little equation for that. And how to find it on the periodic table, it is the decimal number. Usually it's written underneath the element symbol or in small print somewhere. Okay. Yep. So one more time here. If you change the atomic number, you're going to be changing the identity of the element. If you change the mass number, you're going to be changing the neutrons probably, so you change the isotope. And then if you change the atomic mass, I guess that would change the element too. Okay. So obviously, as we were talking with sodium, the number of electrons in an atom is pretty important. The number of protons is obviously important because that determines your element. The number of neutrons is also sometimes important, especially in nuclear chemistry. And so we need some compact way to describe all this. Okay? And so so the easiest way to show how many protons, neutrons, electrons you have in something is to use notation. And the most common way is the symbol notation. So I'm going to use the imaginary element symbol Q. If you're up on the periodic table, you know there's 2 letters of our alphabet that's not included on the periodic table. One of those is Q, and you can figure out the other one. I'll tell you at the end of the video. The symbol, though, has 4 corners. Each corner is going to hold a number that tells you something about the atom. The bottom left one is the atomic number, Z. And again, that's your number of protons. Your top left number is the mass number. And that is your... so if you notice here, your mass number here can never be larger than your atomic number because the mass number always has protons, which would be the same as down here, plus the number of neutrons as well. So your mass number, your top number will always be bigger than your bottom one. They'll only be equal if there's 0 neutrons. The upper right-hand corner is reserved for the charge of your atom, if it has any. So if your electrons are different than your protons, they'll have a charge, +2, -3, or whatever. And then your bottom right number is reserved for subscripts. That's useful in formulas, as you know, as in H2O. The 2 there would tell you that there's 2 atoms in your molecule. Okay? So let's go ahead and work this out and do a couple practice ones here. We're going to write a symbol notation for that. Atom has 12 protons, 13 neutrons, and 10 electrons. So the 12 protons then would go down here on the bottom left number. The 13 protons will be used to figure out the top right number. Top left number, but remember it's protons and neutrons. So we're going to add the 12 protons and the 13 neutrons to get mass number 25 there. And then it only has 10 electrons. Now we're not going to put the number of electrons there, we want to put charge up here instead. And so if it's got 12 protons, that means it has a charge of +12 from the protons. It has 10 negative electrons, so you're going to basically take away 10, so that's going to leave you with the charge +2. Right? And so if you have fewer electrons than protons, then you're going to have a positive ion. If you have more electrons than protons, then you're going to have a negative ion. Right? So losing electrons makes you positive, gaining electrons makes you negative. It's kind of backwards, but that's because the electron's negative. Right? And then we're going to ignore the subscript down there. And so then the last step is to figure out what this element exactly is. The key here is the number of protons, 12. There's only one type of element that has 12 protons. You look on the periodic table and you see that's magnesium. Right? So let me rewrite this here. The complete symbol would be magnesium with 12 protons, 25 protons and neutrons together, and a charge of +2. And that's your symbol right there. It tells you everything you need to know about that magnesium atom. Okay? You go ahead and take a try at number two there, and then we'll compare our answers. All right, we'll start with protons here. 8 protons will go in the bottom left number. We have 8 protons and 9 neutrons. That will go in the top left part. So that's 8 and 9 makes 17. Then lastly, we have 10 electrons. So we have more electrons than protons. So that's -10 and a charge of +8 for neutrons. So this is going to have a charge of -2. And then lastly, we got to figure out what this element is. It's got 8 protons, and so therefore it's oxygen. So this is oxygen. Occasionally you also see what's known as the hyphen notation. What the hyphen notation is, you simply write the name of the atom, so in this case it would be oxygen. You write the hyphen, that's the hyphen notation, and then you put the mass number, oxygen 17. You're probably familiar with carbon-14. It's a radioactive isotope of carbon. It's called carbon-14 because basically that's the hyphen notation. If you notice there's no space for a charge, when you're dealing with radioactivity, you usually don't care too much about the charge, you just care about the number of neutrons, because that determines how stable your nucleus is. Right? So that's notation, pretty simple. Let's go on then and